The first thing we're going to get into is the bearing of different resolution on the render's output. If you'll see here, in the picture that's rendered at 320 by 240 pixels, the stars are way too bright. But if you look at the picture that's rendered at 640 by 480, the stars still just don't quite look right. And if you look at the picture that's rendered at 1024 by 768, the stars look just about perfect. But that doesn't work in this case because we're going to be rendering this section at 4K. And at 4K, you can't see the stars at all. The bearing of this example shows that you want to render your picture at the exact quality that you plan on publishing it at. Although this looks pretty good at 1024, it doesn't look good at all at 4K or 320. So if you're trying to save time matching your colors by rendering at a smaller resolution, in the end, it won't really work. Next here, we have a comparison of rendering this default scene, which we're going to use for the next few minutes, and it compares rendering it on the network with 4 nodes as to rendering it on the local machine, to show that sometimes a network render is just not economical. Here we have a comparison between different versions of Maya. As you can see, the render from the Maya 2014 is significantly faster than the render from Maya 2013, so you want to make sure to match up your software with your hardware correctly. Here we have a comparison of our same scene using 4 different setups. The first one, we're using the 4 network nodes, and we have a render time of 4 minutes with the network discovery. The second render is nearly a minute faster at 3 minutes and 25 seconds, which also uses the 4 nodes but does not include the network discovery. The third render in this case is using the maximum number of network nodes that Maya Mental Ray will allow, which is 5, using the 4 network nodes plus the local machine. It has a time of 1 minute and 58 seconds. And finally, you can see that rendering on the local machine is faster in this situation, as it renders the scene at a mere 37 seconds. Most of the time, though, we won't be working with small scenes like the scene in our last comparison. This is an average classroom scene, and it has about 1.4 million polygons. If you look at the comparison between the rendering on the network render with 5 machines and the rendering on the local machine, you have a difference of almost an hour and a half. It takes nearly 2 times longer to render this large scene with just 1 machine as it does with 5 machines. The importance of checking these different render types is when we're going through our pipeline or our workflow, and you can see that in this section I'm not satisfied with the final render of the classroom scene. It has too much reflection blowout on the floor, and it also has final gather splotches coming out of the light in the back. So I'm probably going to have to change my light settings and my final gather settings before I actually send it off to the final render. This is rendering a master beauty layer, and as you can see, the classroom scene has about 1.4 million polys, and it's being rendered on the 5 machines to get the result of an hour and a half just to check the color or the lighting. This is the scene on the outside of the classroom, which has significantly more than 1 million polygons. This scene, which is checking the depth layer, has about 500 million polygons. And it takes nearly 4 hours to render. Here are a few scenes of the outside of the street in the school scene. If you'll notice here, you can see that when the machine runs out of RAM, it doesn't stop, it just quits rendering sections of the picture, like this wall right here. It's rendered all of the color and the texture on the wall before it, but when it runs out of RAM, it just stops coloring it. A large part of this is because each of these trees has an actual leaf, which renders as a single polygon, and the ray tracing from the light calculates the way that the light interacts with each polygon. Also, these tree leaves are translucent and transparent, so it also has to calculate the translucency, transparency, and ray tracing for each leaf on each tree. This is the entire school scene. Now, if you'll notice, the classroom only takes up a very small portion of the scene. And even in the second scene, we're only shooting from the first house on the block here to the last house on the block here. But we have all of these extra things in our scene because we want to show the sense of depth instead of just painting a background picture. And this makes sense when we look at our reflection. So here we have the last house on the scene. And if you look in the mirror ball here, you can see the sense of depth that we get from the reflection. Now, to check to make sure that the reflection is going to be correct, it took this scene has, again, about 500 million polygons. And in this case, to check the reflection, it says that it in fact took 13 hours. So after I got done checking the reflection, and I decided that I didn't like the way that it looked, I had to go back and render it again at a total time of 12 hours and 44 minutes. Given this render time was only done on one machine, and it did not incorporate the network nodes, this would probably reduce the time to closer to around 6 hours, which is still a very long time when you're looking at the length of time it takes to do the pipeline or the workflow. Next, we're talking about rendering types, which I've covered in other lessons. The first one is the render view, which renders single frames. This can often be used during the workflow to adjust your color or your lighting or your reflection and base how you want to set up the entire scene. You can also use the IPR, but we're going to stick with just the render view and the different types of rendering. Next, we have the batch render. We want to move to the rendering menu in our taskbar here, and then go down to the render tab, and halfway down you'll find the batch render button. This will open up the batch render, which allows you to shoot multiple frames. Next, you can open up the outliner at the bottom by pressing this button here, and it will give you an overview of the batch render as it's taking place. Finally, we have Backburner, which again is under the Rendering tab on the Rendering menu, and it's down towards the bottom. It says Create Backburner Job. We want to do this after, under our Start button, we've opened up the All Programs, gone down to the Autodesk folder, and then found the Backburner program under the Autodesk folder. We would want to open up the Manager and the Monitor to start Backburner before we would create our Backburner job. The last type of rendering we cover here is the .bat render. With this dual Opteron system, it has 32 cores available, and you can run 32 executable files at a single time, which is beneficial in some ways and not beneficial in other ways. Theoretically, each core is able to produce 2.7 GHz, but in reality, each single thread produces significantly less, closer to 0.9 GHz. So, in this case, running 32 executable files is not quite as efficient as running 6 executable files using multi-threading. To look at our comparison side to side, using our default scene that we've used throughout the beginning with these 2 Star Wars model spaceships and around 30,000 particles, the backburner job at 100 frames took about 41 minutes. As you can notice, it only uses about 10% of the processor though. This was run on 6 machines on the network. The batch render, on the other hand, took 3 hours and 46 minutes, and it was also run on the maximum of 5 machines, which is all that Mental Ray will allow you to use. And finally, the executable .bat render took only 10 minutes, running on 6 machines. So, if you look at the comparisons between these different types of rendering to get the same result, each one of them has its pros and its cons. Backburner uses less processor power, so if you're sharing your server with several other users, perhaps Backburner would be more efficient. The batch render is fairly slow, but it also does not put very much strain on the processor or use very much electricity. And at last, the executable .bat render is very fast, but it puts a large strain on the CPU and it uses a large deal of electricity. Next, we're going to talk about large renders. This course was taken from the Gnomon or Genome School in California, but it has way too much information to cover here. So first, we're drawing a forest on the mountain behind Our Lady. In the beginning, we decide that the forest is too sparse, and we beef it up with more trees. So now we've discovered that we have the right amount of trees in our render. After we have our trees figured out, we go ahead and we add some grass and some clouds in the background. Look at the way that the clouds change the overall look of the scene, making it much brighter and changing the actual color of the trees and also the skin of the model. Now that we have the look of our scene correct, then we're going to add some displaced geometry to make a river with a waterfall in the background. This was made in Mudbox. At first though, when we add the displaced geometry into our scene, you can see that it doesn't quite blend with the ground plane for our scene. It has this ugly black line. Once though, we get the displaced geometry properly blended with our ground plane, you can see now that the colors do not match with the original trees and the sky. Each one of these pictures that I've shown you has taken a render time of about 2 hours and 45 minutes render time just to check the texture and the color and the light density. Eventually, I did end up getting my color to match up seamlessly with that of the trees and the sky after about a week of working on this scene file. This scene file has around 3 trillion polygons. This was the end result, where I got the ground plane to match up with the displaced geometry, the color of the trees, and the sky to get the look that I wanted. Now that we have the look correct for this 3 trillion polygon scene, then we're going to add our dynamics. Rendering dynamics is different than rendering background scenes. Here we're using Next Limit's RealFlow to do a particle simulation for our waterfall. RealFlow takes a very long time to render. Here we have a comparison from this course taken from the Digital Tutor's Introduction to RealFlow, course number 6, where we have a simple plane, a gravity daemon, 3 linear emitters emitting liquid, elastic, and dumb particles. I did the comparison on the 3 different types of processors that I use, that being the i7, the Xenon, and the dual Opterons with 32 cores. In this case, the Intel beat out the Xenon and the Opteron as far as speed, rendering 200 frames at 2 minutes and 12 seconds, with the xenon coming in close second at 3 minutes and 24 seconds, and finally the opteron with its 32 cores coming in at a whopping 12 minutes and 55 seconds, thus showing that more cores and higher gigahertz is not always better. I discovered that actually running RealFlow with one single thread significantly increases the render time. But as you'll see in just a second, that is not always beneficial. When we're looking at the rendering for our river and our waterfall scene, after 9 days, we're looking at around 2.7 million particles, and it looks to see that we're going to have at least another 15 days before the beginning of our particle simulation is finished. This render is being done with 32 cores on the dual opteron system. With the vast amount of particles involved in this scene, we want to use the machine with the extra RAM and the multiple cores to handle the workload. As you can see, after 9 days, it doesn't seem to show any slowing in the amount of particles that it's producing per day. Plus, if we notice, the processor has a very aberrant system that it's generating the particles with. We can't, however, render our network render on the network, as you can see here from this demo file under Graphs and Hybrido Space. First, we run our simulation, and it goes through the particles, and we get this melting effect by changing the viscosity of our particles. First, we have to go through and we have to simulate the rendering of the particles to get our initial shapes. Then, in the second part, we can hide these shapes that we use to get our particle simulation. And then we have to render the mesh, which we will actually transfer out to our rendering program like Maya. So we select our particles and we select our mesh, and then we have to simulate the entire simulation a second time. So we go through and press the simulate button. This took about 10 or 20 minutes on the i7 computer. And now we can separate our particles from our mesh. Right here we have the mesh. We're going to give it a smooth shade and change the color to something that looks more like chocolate, so that we have a chocolate rocket. Once we've completed our initial simulation, the mesh simulation can be rendered on the render nodes. But initially, when we're rendering the particles can only be rendered on one machine, and there is no significant increase in time. Here is our chocolate rocket after we've added the mesh to it. This is the mesh that we would send to our rendering program. The way to render on render nodes can be found under the Help menu, under RealFlow Help, which comes with the program. You don't have to get on the internet. And under the RealFlow documentation contents, down under Simulation Network, the first node, the Job Manager and Nodes, it gives you a brief overview of the Job Manager and the Job Nodes, which have to be purchased separately from Next Limit. The Job Nodes cost about $2,000 for every 5 nodes. So in the case of my microcloud, I would probably have to purchase 2 sets or 10 nodes at the cost of nearly $4,000, as compared to RealFlow itself, which costs also about $2,000. The reason for this is it's cheaper to buy 5 nodes than it would be to buy one real copy of RealFlow for each node. Then we would send the mesh to the render nodes, and we would still have to render the particles on our original render.